needed by all living organisms. It has a major role in many natural processes and is vital in countless physical and chemical reactions. The discoverer of vitamin C once said, "Water is life's matter and matrix, mother and medium. There is no life without water." Albert Szent-Györgyi. Water sampling in countless situations can be dangerous, with lakes, rivers, creeks, catchments posing hazardous effects to the human being. Our solution targets one of the most polluted rivers in India. This is a picture of the Yamuna River, which is populated with foam due to its high levels of toxicity. Our problem statement is to research, design, provide a proof of concept of a remotely operable portable device to retrieve water samples from the environment for chemical analysis. So what better way than to design an unmanned aerial vehicle to do the task? I'll be getting my respective team members to speak about each subcomponent of the integrated design. My amazing team consists of Brandon Voon on the water sampling solution, Alex Peterlin for the rotor and aerodynamic design, Henry on the chassis system, Alex Nguyen on the flight control and path planning system, Aaron on the navigation and mission planning system, myself on the power and prognostics health management, and Dylan on the communication and telemetry system. The overall concept will be compared against its technical and economic appropriation, as well as its suitability as a field instrument. Now let's not wait. How does it sample? We have Brandon up next to tell us this.
The ability to conduct water sampling opens up a wide range of possibilities that researchers can investigate and research upon to further understand water composition and potential sources of pollution within the region. This can aid water scarcity issue whereby local community can consume this water knowing that it is safe, clean and consumable. The aim of my portfolio is to conduct a research into current sampling methods that are widely used in the industry and understand how they work. Then improve, design and prototype a better version that is both autonomous and economically feasible to be deployed to a developing country. The system has to be simple, robust and reliable with the use of proper material that will not leach or react with chemical compositions or analytes found in water. In order to achieve this, a design flowchart was made. This acts as a systematic guide for the entire project while being able to identify key design phases. The selection process undergoes the same methodological process in which the best and most suited design will be selected. The selection process includes the use of quality function deployment, PUF matrix, system comparison, and cost comparison. Cost is particularly important in this design project as the system will be required to be deployed to a developing country. As such, a simple cost comparison was made for the different designs based on its manufacturing cost, operating cost, maintenance costs, and replacement costs. The operating cost takes into account the local labor cost for the entire duration of sampling. Adding to that, a 5 years cost analysis was also done to compare its deployment feasibility. A total of 3 design concepts were made. The first design, as seen on the left, is an improved version of the reusable double check valve baler, and a second design on the right uses a pump. Design 1 also has a screw-on top cap that allows the bottle to be accessed easily for cleaning and decontamination. Design 2, on the other hand, features a tube guide channel that acts as a support and guide for the inlet tube to feed water directly into the inlet of the bottle without coming in contact with it. The final and selected design is an improved version of the Van-Down bottle with 1.5 litre capacity. This design features a newly designed closing mechanism that uses a magnet instead of the traditional messenger. This ensures that the triggering of locking pin is almost certain every single time regardless of how deep the sampling is. Besides, it also has a detachable bottle clamp that allows different bottles to be used for different sampling condition and environment. The free space beneath the handle can be used to attach in situ measuring sensors. This includes pressure and temperature sensors. This is a particularly important feature for the sampling in Yamuna River as the pressure sensor will be able to distinguish between foam and water layer. On top of that, the use of these in situ measuring sensors allows for different stratified layers to be identified. Here's a short animation of how the bottle will work. Several tests were conducted on the final prototype. This includes a sampling volume test and a leak test. The purpose of the sampling volume test is to understand the sampling limit of the bottle when being submerged in water. It is particularly important that the bottle is filled completely with very minimal gas pockets as they tend to expand when being retrieved. This will affect the sample content. The purpose of the leak test is to ensure that the bottle provides a relatively tight seal when sampling. As summarized here, the first 2 leak tests failed because of the latex tubing in the middle of the bottle. Through this test, the process of prototyping can be said to be a success where the bottle is able to perform its necessary tasks. However, further testing is still required where the bottle will be put under adverse weather and water condition to allow the operator to fully understand the capabilities of this design. Besides, several improvements can also be made on off-the-shelf components to increase its operational lifetime, to minimize replacement and maintenance. Before I end, how is this autonomous and how will it move?
It is clear to modify our drone to have a water sampling device attached underneath. It would need to accommodate a moderate payload capacity and possess a high level of stability to facilitate the sampling of water. The drone's flight system would also need to be carefully implemented to allow for a medium flight time, as well as include several safety features to protect the drone and drone operators. Using a simple and concise design methodology, a suitable solution was developed which could successfully provide the necessary lift required to comfortably fly the drone whilst maintaining a high degree of precision and safety. This was done using common design methods such as a quality function deployment and a Puise matrix. These tools helped accurately translate the customer requirements into relevant technical specifications, as well as ensure the final design could effectively fulfill them. The first design concept put forward was a quad-rotor drone. This multi-rotor drone exhibits high levels of stability and is easy to operate and maneuver. More importantly, the rotor configuration is able to use its multiple rotors to help reduce the risk of the drone being damaged in case one of its motors was to malfunction whilst in the air. However, this drone configuration suffers from low efficiency due to the increased power needs from the multiple rotors. To become a viable option, this design would need to minimize power consumption to prolong flight time. The second design concept was a single rotor drone. This drone rotor configuration is very efficient, which allows it to carry high payload capacities for extended periods of time. By only using a single rotor, the length of the propeller blade can be easily adjusted to increase the amount of lift produced. Unfortunately, this drone design is difficult to operate and lacks the backup rotors that multi-rotor drones have. To integrate this design, this drone configuration would need to become easier to control and be modified to include safety features to protect the drone from external damage. The final design selected for the flight system of the drone was a hexarotor configuration. This multi-rotor drone is able to meet the medium payload capacity required by using an additional 2 rotors. Furthermore, this multi-rotor configuration benefits from the extra 2 rotors, which can be used to safely guide the drone down in case one of its rotors were to cease function mid-flight. To prove this design could indeed provide the necessary thrust to comfortably lift the drone, thrust calculations were performed. Moreover, to further validate this design, a feasibility study was conducted to outline the initial and ongoing cost over a 5-year period. This hexarotor configuration was shown to be an optimal design solution for the purpose of sampling water using a medium payload capacity. To further improve this design, future recommendations were put forward, which included the addition of propeller guards to increase the protection and safety of the propeller blades. Due to restrictions, future testing was also needed to confirm the practicality of this design in the field. Whilst this hexarotor drone configuration was proven to be a feasible design, the chassis would also need to be modified to allow this flight configuration to be fully integrated.
Functional requirements relevant to chassis design were developed to optimize stability, structural support, and amphibious capabilities, with a QFD analysis revealing additional consideration and weighting to be given to water and chemical resistance, repairability, durability, and ground and water landing requirements. Corresponding design parameters were then constructed to assist in the development of conceptual designs via a morphological matrix. Now, Thesis A identified that heavy lift, waterproof drone frames were not commercially available. However, it also revealed the modification of an existing off-the-shelf drone frame to be more feasible than a fully customized frame. As such, the Turret 960 and ZD 850 were identified to best reflect the design parameters of concepts 1 and 2, with a Puise matrix revealing the ZD 850 to best satisfy functional requirements and ease of modifiability. Foldable propeller arms improve portability, high-strength carbon fibre members reduce weight without compromising structural performance, and a modular system supports repairability. The original ZD850 central housing plates comprise a range of slot and hole configurations to outfit different component integrations. However, the resulting porosity essentially precludes operation in proximity to water. A purpose-built drone such as this doesn't require these integration flexibilities, so a customized watertight central housing was constructed from ABS, with 4 reinforced screws added to ensure waterproofing and ease of access for inspection and repair. Weighing only 61 grams more than the original housing, this supports a feasible modification. Component integration was also designed to align the drone's centre of mass with its geometric centre, thus improving flight stability, and holes were created allowing circuitry to access motors, navigational equipment, and batteries. Carbon fibre members were also sprayed with a UV and water-resistant coating to maximise durability. Landing legs were outfitted with a closed-cell polyethylene pool noodle capable of providing the necessary flotation to support an additional 4 kilograms more than the expected maximum payload, acting to conserve battery power while sampling and prevent loss over deep water bodies in the event of critical failure. The battery was placed upon the bottom rack to lower the centre of gravity from 17 centimetres to 12.5 centimetres above the ground, thus improving stability upon floating. The redesigned ZD850 shown here weighs only 1.25 kilograms and can support an 8 kilogram payload, meaning it is more than capable of carrying the required mass. I will now pass it over to Alex to talk about flight control and planning.
Thank you, Henry. So in my section, I'll be going through 3 of the many hardware and electrical components that will help this whole drone work. The aims in my section were to find a method of manual control, to select the optimal control algorithm for flight stability and maneuverability, to develop a path planning algorithm for optimal trajectory, as well as finding an effective processing unit to process multiple algorithms. So it all starts with a design methodology, where following this framework will ensure my final design is adequate. These are the multiple amount of design parameters that I found, and they all went into a morphological matrix where 3 initial designs were made. So let's get into these concepts. In terms of manual control, the smartphone app has become increasingly popular, where you only need one device for live video broadcast as well as manual control. And it's definitely amazing to incorporate within a product. However, personally developing an application this early in the stages of development does not seem feasible, so a remote control is recommended. For flight control, the algorithm isn't the only component for stabilization. It's the complex synergy between peripherals. So developing from scratch seems very hard, and purchasing may seem more feasible as they're currently very mature and being developed over a decade. So 3 path planning algorithms were placed in the same experimental environment, where the D-Star provided an adequate path but a long processing time. The PRM had the same processing time, however, a more optimal path, and the RRT method had a shorter processing time with an adequate result. The feature cost comparison was made between the high and low level processing units and considered for the final selection. And the concepts and the FRs were compared together through a Pugh's matrix, where overall the third concept was decided, which was the use of a Pixel 4, a Raspberry Pi 4, a remote control, and the RRT method. So let's get into the final validation of the RRT method. To validate this path planner, it was tested with 2 satellite images, and these satellite images were placed into a virtual environment, the green being the starting point and the red being the sampling point. There's no obstacles in this image. So the red path generated, you can see it's very jagged, and it would waste a lot of battery life if the drone was to fly through this path. So we developed a smoothing algorithm, which is in the blue, and it's almost a straight path, which is great for the battery. In the second mission, we incorporated obstacles, which are the trees on the right-hand side of this image, and it was placed into an image processor, put back into the virtual environment, resulting in these blue obstacles. And a path planner was made and produced a definite optimal result. So it was also placed into a 3D environment, however no object data could be incorporated due to time constraints. So to conclude, the radio remote control will be used as the manual controller, the PX4 system will be used as the flight control, the modified RRT method will be used as the path planner, and the Raspberry 4 and the Pixel 4 are used to execute programs. So you might ask now, how does it detect the objects? How does it even conduct the mission? Aaron will answer those questions within his section.
Drones were not smart. So far, we have tried our best to guide them with a safe path and hope they can come back. But obviously, this is not enough. As we're simply along a Yamuna River, we may encounter buildings, people, and other unexpected obstacles. Before we can deploy our drone into public use, we have to address these risks. Knowing this is an application for a developing country, we aim to develop an autonomous navigation system that is robust and reliable, where algorithms and sensors are tested under real-world scenarios. Operational, where minimum training is required for the safe operation of the system. Cost-effective, where local sensors and less complex algorithms should be selected. Transferable, where systems can be easily set up, deployed, and updated on scale. Weight efficient, where less bulky or heavy hardware is prioritized in selections. We propose a methodology based on the system engineering design approach, which primarily consists of a conceptual design stage and a detailed design stage. In the first stage, we conceptualize our design by determining the functional requirements, finding the corresponding design parameters, combining the components into alternative design concept, and finally finding the optimal design. Based on the design concepts, 4 subsystems were prototyped and evaluated during the detailed design stage. This includes a finite state machine-based mission planner, a monocular vision-based sensor configurations, an obstacle avoidance algorithms, and a tracking algorithm for safe landing. Let's demonstrate our result with an example. In typical water sampling missions, the autonomous systems start with the mission planner, where the high-level behavior are managed using the finite state machine. When the mission starts, the planner system will invoke a series of check and analysis before the drone takeoff. Once the drone is ready, it enters the central task control state, where it kickstarts path planning and begins navigating. During the flight, the system continues to avoid obstacles through optical flow algorithm. When the vehicle returns to landing, the downward-looking camera is triggered and the tracking algorithm finally guides the vehicles to a precise and safe landing. To conclude, we develop a finite state machine-based mission planner to handle a variety of situations during a multi-stage water sampling mission. A monocular vision-based sensor configurations that facilitates near-water altitude measurements and a full coverage in field of view. An obstacle avoidance algorithms to detect and avoid obstacles in a critical range of the vehicle. And a checking algorithm to check the landing size and guide the vehicle for the safe and precise landing. The entire system costs $200 in hardware, but runs at 18 Hz in control frequency. As a result, a simple, robust, yet cost-effective navigation system was developed. Now we have the ability to automate the systems. There's another essential component for making all this electronics alive throughout the mission. Here, we'll have Anthony to talk about our power system.
Thank you, Aaron. In the power and prognostics portfolio, I addressed a few things. What is the power source? How will it be diagnosed? And how long will it last during missions? The methodology firstly undertakes a selection criteria of components for power and power management devices. This sets the foundational work for software to be implemented on. Then, we compare against various machine learning methods. Finally, implementing the modeled, trained, and evaluated machine learner into an application of the drone. The power source is compared with 3 types: solar, photovoltaic, hydrogen fuel cells, and lithium polymer batteries. We've selected the lithium polymer battery, which is independent of the weather and can be maintained in our chosen location. Then, 3 power management boards were used for justification: the Mouth Power Cube, CUAV HVPM, and the Holybro PM07. The driven selection was to choose a PM07, as it provided a power fault redundancy, senses multiple readings such as voltage and current, and was the most economically affordable at $66, which is the lowest of the cost options. Finally, for the prognostics, 9 different machine learning methods were built, modeled, and evaluated. For predicting remaining useful life, I've compared each against its accuracy and computational resource required to justify an appropriate solution. The final justification is the decision tree regression, with the need of only 0.007 seconds to train and an accuracy of almost 100%. Here is a live stream of how the battery is monitored with voltage and current, as the decision tree also predicts the remaining useful life of the battery during the flight. All these design considerations are housed in a software architecture as a preemptive method to safeguard the user from damaging the battery, preventing over-maintenance and sustaining the uses of the drone. But how does it all communicate? We have Dylan next to explain the communication system.
Thanks, Anthony. The aims and objective of the communication component is to create a robust communication structure to be used by the UAV. The methodology for design is to first determine the requirements needed for the communication system. After that, the radios will be selected and a material will be chosen to house the components. The second part of the design is to optimize it for range. The autonomous radio selected is the whole Libre transceiver. This radio was selected as an interface with the flight controller system, as well as it uses Mavlink protocols, which is used by the mission planner. For the manual radio, the R12DS radio was selected. This radio met all the required performance parameters. The deciding factor for this radio was that it has an inbuilt pairing system which allowed it to be used with tuned RC controllers. The vision radio selected is the TS832. The range and data transfer of this radio far exceeded what was expected. The low latency of this system also allows for streamless video stream. Next, the material will be selected for the housing, with a focus on water resilience. ABS was selected because it is lightweight, water resilient, and very easy to work with. The final design of the housing can be seen here. The parameters that affect the range of the transmission include the power of the transmission, the sensitivity of the radios, as well as the gain of the antenna. The only feasible parameter that could be changed from this list is the gain. However, increasing the gain would decrease the reception area of the antenna. A workaround of this is the antenna tracker. The antenna tracker processes GPS data and repositions the antenna so that it's constantly facing the UAV. This is a cost-effective method of maximizing range. A simulated test flight was conducted where the UAV flew in a triangular path. The GPS data was then collected and passed into the control algorithm. This was the generated control signal over the mission time. The control value is sinusoidal, which reflects how the UAV moved during the mission. This validates the control algorithm developed for the tracker. Some future work for this project would be physically manufacturing the components to test the strength and water resilience of them, as well as testing the range capabilities of the antenna tracker with the radios. I would like to present the complete integration of all our parts.
As you can see here, this is the final integrated design by DIP. It is a 6-arm hexacopter made of carbon fiber, modified to be waterproof. The pitch of the blades have also been modified to increase airflow efficiency, and the Van Dan bottle has been modified for water collection such that the foam doesn't get into the water sample. The implementation of a finite state mission planner allows for the automation of this whole system, where we use the Raspberry 4 that allows for the synergy of camera, sensor, path planner, power modulator, flight control, and radio data for mission completion. As you can see here, this is the schematic of the electrical components, where the battery is connected to the PM07, which predicts the remaining battery life, and it also powers the flight controller. Cameras, sensors, and radio are connected to the Raspberry Pi such that the data can be used in these algorithms, and the Raspberry Pi is connected to the flight controller for transmission of data for mission execution. Furthermore, as Dylan mentioned before, the antenna tracker was incorporated at the ground control that tracks the GPS coordinates of the drone to overall increase the signal strength. Now you might wonder, how much does this all cost? And is this a waste of money compared to the current water sampling methods around right now? Brandon will continue with his section, where he conducts a feasibility analysis.
To understand the feasibility of this solution, the manual sampling method will be used as a reference. The initial and ongoing costs of both methods will be broken down and analyzed. The initial cost of the autonomous solution involved several components such as the power of the drone, the sampling system, communication, chassis of drone, flight control and path planning, navigation and mission control, and rotor and aerodynamics. The initial costs incurred for these components are mostly related to the programming of software to operate the drone. The ongoing costs incurred would mainly be for the system maintenance of software and component replacement of hardware. Besides, labor costs, insurance, and cleaning will also be taken into consideration. While the initial cost for the manual sampling method would be the cost of the sampling bottle only, the ongoing cost would be the cost of labor, insurance, cleaning, and boat hire. A bar chart was used to summarize these values, whereby the total initial cost for the autonomous sampling is 49,000 and for the manual sampling at 180. The ongoing cost for the autonomous sampling would be 167,000 compared to 478,000 for the manual sampling method. The huge difference in initial cost is due to the additional number of operators required for manual sampling and a higher percentage of insurance required due to the higher risk susceptible to the operators while on the job. An incremental cost analysis was also conducted to understand the total cost incurred to manufacture a second drone for future reference if a larger scale operation requires the use of more drones for simultaneous sampling in different locations. The cost of a second unit onwards would be 7,000 with the ongoing cost of 3,500. The significant reduction in cost for the subsequent drones come from the software aspect whereby all drones manufactured can and will use the current software as the first. As seen, the capital cost for the autonomous sampling method is extremely high. However, the savings on ongoing costs when compared to the manual sampling method would enable the operation to run for at least another 4 years. I would like to pass the remaining time to Henry to talk about the social and environmental impacts of this solution.
A California study found that for package delivery, drones emitted 54% less greenhouse gases than trucks. With traditional sampling techniques in the developing world typically involving two-stroke powered boats, these emission savings are undoubtedly higher than 54%. However, researchers found drone activity can affect wildlife, with resulting physiological and behavioural stresses potentially leading to higher energy expenditure, decreases in reproduction and survival rates, and space use changes. It is recommended a biodiversity analysis be conducted prior to sampling to identify large endangered birds of prey who are prone to fight or flight responses and attempt to mitigate potential harm. Appropriate actions following identification of unhealthy water systems promotes long-term environmental health benefits that will see improved biodiversity, sanitation, water purity, and sedimentation, leading to significant decreases in the number of waterborne diseases that kill millions of animals and humans every year. Water access improvements also reduces developing nations' reliance on aid packages and promotes opportunities for women who are often responsible for collecting water, taking time away from work, school, and family, and thus assisting in the cycle of poverty. Implementation of a drone sampling program would also upskill the workforce and create a range of new jobs. Overall, the environmental and social benefits resulting from drone sampling far outweigh the potential detriment. I'll now pass you over to Aaron.
Thank you, Henry. To summarize, Yamuna River in India was selected as a representative region for analysis throughout the project. After a comprehensive review of related literatures, we decomposed the system into a mechanical system and an avionics system. Each subsystem was developed through a complete engineering design process, subject to the requirements and limitations set out by the user in developing countries. For our mechanical systems, we have developed a novel horizontal sampling mechanism, a hexarotor configurations with optimized propellers, a lightweight chassis design that facilitates amphibious operation. For our avionics systems, we have integrated a flight set using Pixel 4, Raspberry Pi 4, and a radio remote controller. A complete autopilot using the state-of-the-art vision-based navigations, finite state machine mission planning, and rapid exploring random tree path planning was developed. In addition, we have also designed a learning-based prognostic algorithm and an antenna tracker to improve our power management and communication system. The integrated solution has demonstrated promising capabilities in sampling water autonomously in Yamuna River, while requiring significantly less cost and faster than most existing techniques. In conclusions, as a result of this project, we have successfully developed an autonomous water sampling UAV system that has a high potential in improving the water resource management in developing countries.